So first of all, welcome to this year's Chen-Jung lecture series. And so before I introduce the speaker and before the speaker starts talking about her talks, so let me introduce the president of the Mathematical Society of the Republic of China, Professor Lai. Please. Do you want to say a few?
I have to say a few words. Okay. I'll make it short. Okay. Let Dr. Chen to introduce Professor Maria Chudnovsky. I just want to very quick quotation about Professor Chudnovsky. I try to serve the web. That's she has a lot of things. She's an intrepid mathematician and also public figure. Okay, she also did a commercial, TV commercial, as a smart mathematician, right? So, other than that, if you are quoted by some expert in graph theory, if you are young mathematicians, young mathematicians are called promising. Okay, if they are expected to become half good in 10 years as Maria is now, then it's called promising. Maybe I can't explain Chinese. 如果你年轻的数学家，如果你10年之内能够变成他的一半的好的话，那你就是非常的 promising。不过that was said in 2004, but now it's more than 10 years. Now it's only a quarter of good as Maria. Okay. However, I don't have to go into this category, a comparison principle, because I'm more than 10 years older than you. Okay. Thank you very much. Thank you for being here.
Okay.
So we have a gift for you. Okay.
Stand in the middle here. Take a seat. Then we take this. I'm not sure why.
Good.
Okay. Okay. Thank
Okay.
you. Thank you.
Thank you very much. There's only one problem. I muted my microphone and I can't unmute it. Oh, maybe I succeeded? Is it better? Okay, good.
Okay.
I won't touch it anymore.
Okay. So, thanks to the President Chen Lai for his introduction. So let me say just a few words about this lecture series. So this lecture series is created by the Mathematical Society and also Academia Sinica Institute of Mathematics in honor of Professor Chen-Jung, who served as who was born in 1918. I'll try to keep it short. Okay, he was born in 1918, and then he got his education in Japan. After the World War II, he came back to Taiwan, and at that time, under the harsh condition, he was one of the very few active research mathematicians. But one of one of the things that he cared very much about is the education and the mathematical development of mathematics in Taiwan. And so this is why we have decided to create this lecture series in his honor, and to hopefully to continue his endeavor to improve and enhance mathematical research in Taiwan. So this is the 7th installment of this lecture series, and we are very happy today to have that Professor Maria Chudnovsky from Princeton University could be the 7th speaker. Professor Chudnovsky, she is famous for the solution of the so-called strong perfect graph conjecture, which before now is a theorem. And she was awarded the Fulkerson Prize in 2009, and also the so-called Genius Award in 2012. This is a MacArthur Fellowship. And I believe that she is so far the youngest speaker for this lecture series, and will probably remain so for some time, I believe. And also, certainly, she is the first female speaker, and so let's welcome Professor Chudnovsky.
Well, thank you very much for inviting me, and thank you for coming to my talk. It's a pleasure to be here. It's my first time in Taiwan, and I'm very excited. I have a big sightseeing afternoon planned tomorrow, but I'm told first I have to give talks. So it's going to be a series of 3 talks. The first one is sort of a little bit of everything, and then and also more background and history and things that happened about 10 years ago. And then for my next 2 talks, I'll talk about things that I'm actually working on right now or close to right now. All right, so I'm a graph theorist. I think about graphs. Graphs have a graph consists of a set of vertices and a relation on the vertices. So 2 vertices can be in an edge or not in an edge. And there are 2, or to say it more simply, 2 vertices can be adjacent to non-adjacent. And there are 2 parameters that graph theorists think about. One is the chromatic number of a graph. That means you want to assign a color to every vertex, and you want to do it in such a way that adjacent vertices get distinct colors. So you could try and give every vertex a different color, but that's not the point. You're supposed to do it with as few colors as possible. So the smallest number of colors you need in order to color the graph is called the chromatic number and denoted by chi of g. And then there's a related parameter called the clique number. So what's a clique number? A clique in a graph is a set of pairwise adjacent vertices, and the clique number is the biggest size of a clique. So if you think about it for a minute, the chromatic number is always at least the clique number, because if you have a clique of size 10, that means there are 10 vertices all pairwise adjacent. So you must color them all. You must color each of them with different colors. So you need at least 10 colors, and now replace 10 by k. Okay, so chi is at least omega. That's good. So now let's think about the equality case, right? In math, if there's an easy inequality, what you're going to do is that you're going to study equality cases. So we're going to study cases of equality. When are chi and omega the same? And it turns out there's the same in many nice situations. For example, there's the same for bipartite graphs. So you know what the bipartite graph is. It's a graph where you can partition the vertices into 2 parts, and all the edges go between the parts. Right? So then you can color with 2 colors. You color this part 1 and this part 2, and then the clique number is 2, because you can't fit a triangle into this structure. Complements of bipartite graphs. So that's a little more complicated. What that means is you take 2 cliques, right? You take 2 sets where all the edges inside are present, and then you put some edges between them. So this is much harder to see, but it's still true that the clique number and the chromatic number are the same, and that's actually a theorem of Koenig from the early 20th century. Comparability graphs. So what's a comparability graph? You start with a partially ordered set, and you make a graph where the vertices are the elements of this partially ordered set, and 2 vertices are adjacent if the corresponding elements are comparable. So then what's the chromatic number? Let's do clique number first. So what's a clique number? It's a bunch of elements in the partially ordered set, all pairwise comparable. In other words, we call it a chain. So the clique number is the length of the biggest chain, the biggest length of a chain. What's the chromatic number? So you need to color the graph. So that means you need to cover the vertex set with sets with no edges inside, right? Each color is a set of vertices with no edges inside. So in the partially ordered set, you want to cover the elements with sets so that no 2 elements are comparable, which we call antichains. So the question is it true, or the statement is, it is true that the length of the biggest chain in a partially ordered set is the same as the number of antichains you need to cover. And it's true because just take the minimal elements, take the next minimal elements, and so on. Okay, so these are all nice examples. So one might think that it's a good question when are chi and omega the same, because it somehow separates nice graph classes from not nice graph classes. Except here's an unfortunate example. So take your favorite graph with at most 99 vertices, and take this joint union with a complete graph of size 100. A complete graph just means a graph with all edges present. So then what happens? Well, the clique number is 100. Here you see a clique of size 100. The chromatic number is also 100, right? So you color these with colors 1 through 100, you color those with colors 1 through 99. But somehow I didn't learn anything about what's going on here, right? All I learned is that in this example, in this graph, there's a component which is a huge complete graph. But right, I mean, somehow that's not informative, right? If there's a component not talking to anybody with some degenerate property, we say we didn't learn anything. Right? So okay, so what we want is, it was a good start, right? We got many nice answers, and then we got this answer we don't like. So what we want is a better question. We want to refine the question when are chi and omega the same, so that the nice answers are still there, but the answer that's not nice is no longer there. And this was done by a French mathematician, Claude Berge, in 1961. He proposed the definition of a perfect graph. So what's a perfect graph? It's a refinement of saying chi and omega are the same. So for a graph to be perfect, you need that chi and omega are the same for the graph and also for all its induced subgraphs. An induced subgraph just means you delete vertices. So however you delete vertices, chi and omega remain the same. Here's a more formal definition of an induced subgraph, and I'll say it just because all my talks will be about induced subgraphs, so it's worth spending 45 seconds on defining it exactly. So what's an induced subgraph? H is an induced subgraph of G. If the vertex set of H is a subset of the vertex set of G, so we said we're allowed to delete vertices. And then an edge is an H if and only if it was there in G. Right? So if I delete a vertex, I must delete all the edges that are incident with this vertex. But I'm not allowed to just delete edges. I'm not allowed to say, oh, these two guys, they were adjacent in G, but in H I'm going to make them non-adjacent. That's not an allowed operation. So let's do an example. So here's the graph G. This is an induced subgraph of that, because to get this from that, you just delete the middle vertex. This is not an induced subgraph of that, because to get this from that, you would need to delete these two edges, and that's not allowed. Right? You're not allowed to delete edges. You're only allowed to delete vertices, and as a result, delete edges incident with them. Okay, so now we know what the induced subgraph is. Now we understand what being perfect means. Chi and omega are the same for the graph in all its induced subgraphs. So then what happens here? Well, in these first three examples, if you take induced subgraphs, you stay in the class, right? If you started with a bipedal graph and you deleted some vertices, you still have this partition into two parts and the edges go between them. It's the same for complement bipedal graph, same for comparability graph. Deleting vertices just means deleting elements from your partially ordered set. But here the situation is different. If I delete these vertices, then in here, maybe chi and omega are the same and maybe they're not. And depending on that, the graph will be perfect or not. So somehow I get to learn what's going on there. All right, so that's perfect graphs. And so people started thinking about perfect graphs. It turned out it's a nice concept. It turned out it was a good definition. Now, what does it mean for something to be a good definition? How can you tell if this object you just invented is it good or bad? And I think one test is, does it have good properties you didn't expect? So you define this object in some context, and wonderful, it solves the problem you had in that context. But does it have any other properties that just that do not immediately come from the context you defined it in? And if it does, then it's probably somehow a nice, beautiful thing. And if it doesn't, then it's probably like a technical tool you made up for the particular thing you're thinking about. And so it turns out perfect graphs are in the beautiful category, because they do have lots of, what seems to me, unexpected properties. So the first, so I listed some of them here. This is by no means all, but these are my favorites. So the first one is not an unexpected property. They generalize many theorems in graph theory. So for example, the fact that in a complement bipedal graph, the clique number, the chromatic number are the same, now we can say it in the language of perfect graphs. We can say complements of bipartite graphs are perfect. There's another theorem of Koenig's that you can also, it used to be, some theorem about coloring. Now you can say this graph is perfect. The theorem about posets, right? That's a little bit more surprising, maybe. That the theorem about posets covering with chains and covering with anti-chains, using as many as the longest chain. Again, you can now say comparability graphs are perfect. So it's, there was a body of knowledge that we had, and now you can say it in this language. That's a good start. So the second, but like I said, that's not surprising, right? It's a word we invented to mean chi and omega are the same, so now we can use it. Property 2, on the other hand, is more unexpected. So it turns out there are problems that you can solve that are NP-complete in general, right? So NP-complete means most likely don't have an efficient solution. But if you know that the input graph is perfect, then you can solve them in polynomial time. So what problems? For example, finding the biggest clique, finding the biggest stable set. A stable set means a set of vertices with no edges inside. Finding an optimal coloring. All these things, if I give you a general graph, it's NP-complete. If I give you a perfect graph, then you can do it in polynomial time. So that's kind of amazing, I think. Here's a third fact that is somewhat related to the second. So there's something called the stable set polytope of a graph. And what that is it's a polytope that consists of all vectors that give you dot product at most 1 with characteristic vectors of cliques, right? So you're thinking about, R to the number of vertices of the graph, and you want to know which vectors, right? And then you think about characteristic vectors of cliques, meaning you put 1 if the vertex is in the clique and 0 if it isn't. And now you start thinking, what vectors give dot product at most 1 with those? So one example of such a vector is a characteristic vector of a stable set, right? Because what's the dot product of characteristic vectors of sets? It's just their intersection, the size of their intersection. If I have a clique in a stable set, the size of their intersection is at most 1. So characteristic vectors of stable sets have this property, and then all their convex combinations have this property. And is there anything else? And the answer is that in general, yes. But in perfect graphs, no. This polytope, its extreme points are just the characteristic vectors of stable sets. So that's kind of a surprising fact. And so because of statement number 1, graph theorists think that perfect graphs is a concept in graph theory. Because of statement number 3, people who do combinatorial optimization think that perfect graphs is a concept in combinatorial optimization, which was very lucky for me because I had a job in the in a combinatorial optimization group for 9 years. But anyway. So, okay, so maybe I convinced you that perfect graphs are good for you in some sense. And now the goal of the next 25 minutes or so is to try and understand what perfect graphs are. And the first question is, well, what graphs are not perfect? Maybe all graphs are perfect. Chances are no, but let's come up with some examples of graphs that are not perfect. And so here are 2 families of examples. The first one is an odd cycle of length at least 5. So a cycle means you put a bunch of vertices in a circle, and you make consecutive ones adjacent and non-consecutive ones non-adjacent, and the length just means how many vertices you put on the circle. So, all right, so I put an odd number of vertices on the circle. Now I claim this graph is not perfect. In fact, chi and omega are different. Let's see why. Well, what's omega? What's a clique? What's a clique number? The only sets of pairwise adjacent vertices are consecutive pairs, right? You can't find 3 vertices that are pairwise adjacent. So the clique number is 2. What about the chromatic number? Well, if you take an odd cycle and you try to color it with 2 colors, you'll quickly notice that you can't, right? You go 1, 2, 1, 2, 1, 2, and then you're stuck. So the clique number, the chromatic number is 3. So omega of C2n plus 1 is 2. Chi of C2n plus 1 is 3. So they're different. So it's not perfect. Except I need to be a little bit careful, because when n is 1, then C2n plus 1 is this, and then it's not true that omega is 2, right? I cheated you, I went too fast. I mean, maybe I didn't cheat you, but I did go too fast. So we need to say, as it says there in the slide, n is at least 2. And then that's not perfect. Okay, so that's one infinite family of graphs that are not perfect, but you know, I have to agree, it's a nice infinite family. What about this? So that's another family of graphs that are not perfect. And this is what's called complements of odd cycles. So I'm going to eventually show you this definition, but let me tell you now informally. The complement of a graph just means you change all the adjacencies. Or you start with a graph, and now you build a new graph that you call the complement of the graph you started with. If two vertices are adjacent in the new graph, if and only if they're non-adjacent in the old graph. And again, I'll say it again later, but for now, let's just think of this as, so the complement of an odd cycle means you put 2n plus 1 vertices on a circle, and you make consecutive ones non-adjacent and non-consecutive ones adjacent. Right? So for example, if you do it with 5 vertices, then you're going to have this graph, which, if you think for a second, it's actually the same graph as this graph. Right? Just number the vertices differently. So we learned that C5 and C5 complement are the same graph. But in general, it's not. In general, it's a completely different graph. Okay, so for example, this in the picture is C7 complement. So now, what happens here? I claim that's another family of imperfect graphs. And the reason for that is, well, let's see, what's the clique number? How big a clique can I get in this? So in a clique, a clique cannot contain 2 consecutive vertices, right? Because consecutive pairs are non-adjacent. So I have 2n plus 1 vertices, and I'm trying to build something that's not allowed to contain 2 consecutive vertices. Then I better go, the best I can do is go yes, no, yes, no, yes, no, no. So the clique number is n. And what about the chromatic number? So what does it mean to color this? It means that you need to partition the vertices into color classes, each of which is a stable set. And the stable sets here, how big are they? Well, it's only size 2, right? The only stable sets you have are consecutive vertices, consecutive pairs of vertices. So then I'm trying to take 2n plus 1 vertices and partition them into subsets of size at most 2. Well, how many subsets do I need? At least n plus 1, right? That we know. So chi is at least n plus 1. And they're different. And again, I need to be a little bit careful, because if I look at this graph, if I say n is 1, then this is not true. Okay, so these are 2 families of graphs that are not perfect. And it turns out that that's it. So let me tell you, in some sense. So let me tell you this more slowly. When Claude Berge defined perfect graphs, he made 2 conjectures about them. He called one of them the strong perfect graph conjecture, and one of them the weak perfect graph conjecture. The weak perfect graph conjecture said that the graph is perfect if and only if its complement is perfect. And again, remember, taking a complement means changing all the adjacencies. The strong perfect graph conjecture says a graph is perfect if and only if it does not contain an odd cycle of length at least 5, and it does not contain the complement of an odd cycle of length at least 5 as an induced subgraph, meaning you can delete vertices to create one of these or one of those. So let's think about this for a minute. So first of all, if you believe this, if you believe the strong perfect graph conjecture, you should believe the weak perfect graph conjecture, because the strong perfect graph conjecture is clearly, is a statement independent, invariant undertaking complements. So okay, so that's step 1. Step 2 is, one direction of the strong perfect graph conjecture is easy. If I have a graph that's perfect, then however I delete vertices, I should get a graph where chi and omega are the same. So certainly it shouldn't contain these or those. The only question is it really all? Are there some other minimal imperfect graphs? Are there some imperfect graphs that don't contain odd cycles or their complements? All right, so Berge made these two conjectures. Now, I have to say, I'm curious sort of about history here. So he made two conjectures, one implied the other. Is it because he didn't quite believe the stronger conjecture? And he wasn't sure. He said, well, maybe this is false, but maybe that's still true. Or was it sort of clever? He said, oh, that's too hard. People would not want to think about it. But that one, there is some chance people will be thinking about. So I better write them both down. So I don't know what the answer is. I should ask somebody, but I don't know. So anyway, so by now these are both theorems. The first one was proved by Lovász in 1972, when he was 19 or something. And the second one was proved much later by Neil Robertson, Paul Seymour, Robin Thomas, and myself. So I'll talk some about this proof. I won't talk about the proof of the weak perfect graph conjecture, but it's sort of interesting. So Lovász had this proof, and it's hard, and you learn a lot about math and about polytopes, and sort of develop this beautiful theory to prove the weak perfect graph theorem, and it's hard. And then some years later, Gasparian came, and he gave a proof of this theorem in 2 pages. You can, I teach it in my undergraduate course. It's no problem. You can teach it in 45 minutes, maybe an hour. It's sort of very clever, very lovely, and you don't understand anything. It's just this beautiful, clever trick. You have no idea why this trick should possibly work, except it does. So somehow, two extreme examples of proofs for one theorem. But that's all I'm going to say about the weak perfect graph theorem. So now let me move on to the strong perfect graph theorem. So first of all, I want a definition. I want to say a graph is Berge if it doesn't contain as an induced subgraph a node cycle with length at least 5, and it doesn't contain as an induced subgraph the complement of a node cycle of length at least 5. And you can see why I would want a word for it, because if I kept saying that, that would take my whole talk. So that's Berge. And just a point of information, it is not Claude Berge who decided to call these graphs Berge graphs, it's Vašek Vatal. So, okay, what do Berge graphs have to do with this theorem? It says a graph is perfect if and only if something, 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 and now we call the something, 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 it's Berge. All right, so here it is written down again. The strong perfect graph theorem, the strong perfect graph conjecture says that Berge and perfect are the same. And we already discussed that if something is perfect, then it must be Berge. So now we need to do the other direction, prove that Berge implies perfect. And so this conjecture was open for 40 years before it was solved, and people were working on it. It wasn't sort of one of these problems that people thought about it for a year, decided it's too hard, and put it aside. There were many papers that made partial progress of various kinds, and there were 2 sort of main strategies that people were trying. One was let's try and think about a minimal counterexample. So let's look at a minimal graph that's Berge and not perfect, and let's try and prove everything we possibly can about it, and hopefully in the end we'll prove so much that some 2 things will contradict each other, and then that means there is no such graph. So that was one approach. And the second approach was let's step away from our goal for a minute, and let's just try and understand Berge graphs. Let's try and prove a structure theorem for Berge graphs. If I can really, prove a theorem that gives the complete construction, complete characterization of Berge graphs, then presumably with this theorem I can prove anything I want about them, right? If I know, here's 20 classes of them and here's a way you can glue them together to make another Berge graph, whatever property I'm interested in, I can check, do these constructions have it or not? Yes?
Can you tell us why this guy made this kind of conjecture? Because even the statement is non-trivial, right? It's highly non-trivial, so how he gets it?
I think only he knows.
Only he knows, okay.
I think it's very hard to say why somebody came up with a conjecture, right?
Yeah.
Somebody who's not you. Okay. So anyway, so there was progress of both kinds being made, and I'm going to tell you that eventually the proof was 80% this and 20% thinking about the minimal counterexample. So somehow it was, as usual, a compromise. And I'll tell you some more details about that. right, so just to kind of focus it, what I'm going to do now is talk about the proof of the strong perfect graph conjecture. Now, it's a 150-page proof, so obviously I'm not going to do any details of anything, but I'll tell you roughly how it works, so that, you know, after this you have some idea. So here's a winning triple of theorems, or maybe I should call them meta-theorems, because these are not actually theorems. They're kind of molds for statements. So if I could prove any triple of theorems that fits into this mold, I would be done. Let's see what the mold is. So the first theorem is every Beige graph is either basic or admits a useful decomposition. The second theorem is all basic graphs are perfect. The third theorem, and so, you know, theorem 1 and 2, they're just sort of honest structure theorems. This is what theorems look like if you're trying to construct a class of graphs. Now, theorem 3 is the 20%. It says if a graph is Beige and not perfect, and it's as small as possible with this property, then it does not admit any decompositions from theorem 1. Right? So this is obviously tailored to prove the strong perfect graph conjecture. So let's just quickly see why this triple would allow me to prove the strong perfect graph theorem. So suppose the strong perfect graph theorem is false. Let's look at the smallest counterexample, as few vertices as possible. So then it's a graph that's Beige and not perfect. Because it's Beige, I can apply theorem 1 to it. So that means either it's basic or it admits a useful decomposition. If it's basic, I get a contradiction to theorem 2, because it's not perfect. And if it admits a decomposition, then I immediately get the contradiction to theorem 3. That's what theorem 3 was designed to do. So, all right. So anything that looks like this, right, you would prove the strong perfect graph theorem. And now, and in fact, so that's exactly what happened. We proved the triple of theorems like that. And what I'll do now, I'll tell you the original triple, and then I'll tell you another triple which is a little bit shorter to prove. So what do I need to do in order to turn these molds into theorems? And to tell you what basic graphs are, and I need to tell you what useful decompositions are, and then these become theorems. So that's what I'll do now. What are basic graphs? So many of these words I've already said, but they were kind of in the introduction, so it didn't matter what they meant, and now I'm actually going to define them. So there are 5 classes of basic graphs. The first class is bipedal graphs, so that means you can partition the vertex set into 2 parts, and the only edges are between the 2 parts. Right? In each part, there are no edges. Second one is complement bipedal graphs, and this is the lucky moment when I show you the definition of the complement of a graph. So G complement is the graph with the same vertex set as G, and 2 vertices are adjacent on G, if and only if they're non-adjacent on G complement. So complement bipedal graphs. Now, what does that mean? So if I complement this, this becomes a clique, this becomes a clique, and there's still some edges in between. So that's this picture. Line graphs of bipedal graphs. So what's a line graph? A line graph I do not dare define without writing. So basically the line graph of a graph records the intersection pattern of edges. Right? You start with a graph G, and its line graph L of G has vertex set, which is the edge set of G, and then 2 vertices in the line graph are adjacent if the corresponding edges share an end. Right? So for example, if you start with this graph, so the edges are 1, 2, 3, 4, 5, 6. So let's construct its line graph. The vertices will be 1, 2, 3, 4, 5, 6. And now 1, 3, and 5 pairwise share an end, so they're all adjacent. 2, 4, and 6 pairwise share an end, so they're all adjacent. And then 1 and 2 share an end, they're adjacent. 3 and 4 share an end, they're adjacent. 5 and 6 share an end, they're adjacent. And no other pair shares an end, so this is that. Okay, so that's line graphs. And so the next basic class, the next class of graphs that they call basic, is line graphs of bipedal graphs. Right? You take a line graph, you take a bipedal graph, you take its line graph, that's a basic class. And it's not hard to check that they're Beige. complements of line graphs of biptype graphs. So this, we already know all the words, you just need to parse it. So you start with a biptype graph, you take its line graph, you take the complement, and that's a basic class. Okay? And the last one is something called double split graphs, which I don't want to say exactly what they are, but it's some other explicit construction of graphs. Now, there's a story about this class. So, by the way, the first four classes, you know, like I said, people were working on this problem, and it seemed that, you know, you should try and prove a structure theorem for Bayes graphs, and it was pretty clear that biptype graphs, their complements, their line graphs, and those guys should play a role, should probably be basic classes. And so, as you know, when my team was working on this problem, that's what we were trying to do, to prove a theorem where these four are the basic classes, and we did. We're very happy. And then when we started to write it down, it fell down. And the reason it fell down is because there's one place where you're hoping you'll get a decomposition, but you don't. Instead, your graph grows to be one of those. So that was a bit scary, but it worked out. So anyway, so this is, I mean, this is not a class of graphs that I've ever seen in any other context. It's just a fix for a theorem that fell down, but it's the truth. Another thing to think about, so we're trying to prove a theorem that's invariant under taking complements, right? Being Bayes is invariant under taking complements, just by definition. Being perfect is invariant under taking complements by the weak perfect graph theorem. So then anything you're proving should be invariant under taking complements, right? If something you proved is not invariant, that means you proved the wrong thing. And so we have biptype graphs and their complements, line graphs and their complements, then we have a fifth class. So it's a little bit worrying when something is supposed to be invariant under taking complements, but there is an odd number of them. But it turns out that double split graphs are their own complements. So that's why it's not a disaster. All right, so these are the basic classes. And by the way, so we need this theorem 2 that says all basic graphs are perfect, and it's true. For biptype graphs, it's clear. Those three are theorems of Koenig, and this one, you know, you can just check it. Like I said, it's an explicit construction. It says, you know, you take 2k vertices and you do this and you do that. You know, you put an edge here, don't put an edge there, so you can check that they're perfect. So okay, so we got theorem 2 down. Yes. No. Yeah. Okay, so now I need to tell you about decompositions. And the decompositions are, we have skew partitions and two joins. So I'm going to tell you what they are. So for a graph that meets a skew partition means you can partition the vertex set into two parts, A and B, so that, into four parts, A, B, C, and D, so that every vertex in A is adjacent to every vertex in B. There are no edges between, and there are no edges between C and D. That's a skew partition. Now, one nice thing about the skew partition is that it's complement invariant, right? Because if you delete A plus B, you get a disconnected graph. If you delete C plus D, you get a graph that's disconnected in the complement, right? Two sets that are, you know, everybody here is adjacent to everybody there. You take complements, that's a disconnected graph. So, you know, so that seems like you're proving the right thing for perfect graphs. It's a decomposition that's invariant under taking complements. Two joins are not like that. Two joins are, they're not invariant. So, okay, let me tell you what a two join is, and then I'll tell you they're not invariant under taking complements. So what's a two join? You partition the vertices, so let's first partition them into two parts. One part is called top, and that's A1, C1, and B1, and one part is called bottom, that's A2 and B2 and C2. And then the rule is that top and bottom don't talk to each other freely. So everybody in A1 is adjacent to everybody in A2. Everybody in B1 is adjacent to everybody in B2. And there are no other edges from top to bottom. So if you construct, you know, a matrix of adjacencies, top versus bottom, it's a rank 2 matrix. So there's something simple going on between top and bottom. So I mean, that's a nice thing. But the thing is, if a graph admits it to, okay, so that's two join, then, you know, your graph could admit a two join, or the complement of your graph could admit a two join, and both of these are things that can happen, and it's not the same, right? For skew partition, the graph admits a skew partition if and only if its complement admits a skew partition. But for two joins, it's not like that at all. So in some sense, two joins are, you know, not as nice as skew partitions. Now, let's see. Okay, so let me talk about this a bit more. So now this is an illusion. Now let's go back to theorem 3, right? I told you what the decompositions are. And now I need to prove that minimum counterexample cannot admit the decompositions. So for two joins and complements of two joins, you can do it. It's a theorem of Cornelius and Cunningham, and it's a nice theorem, but it can be done. For skew partitions, now we also know that the minimal counterexample to the strong perfect graph conjecture does not admit a skew partition. But that's only because we know there is no minimal counterexample to the strong perfect graph conjecture. That we prove the strong perfect graph conjecture, so nothing can happen in the minimal counterexample. So then, how are we going to use this skew partition? Well, it turns out you don't need the most general skew partition. You can throw in another condition, something called a balanced skew partition. And then for balanced skew partitions, you can prove. I'm sorry, I'm going in the wrong direction. You can prove this theorem. So if the useful decompositions are two joins and balanced skew partitions, then you can prove this theorem. And again, balance just means some skew partitions are balanced, some are not. But we don't know how to prove this theorem for all skew partitions, except by saying there is no minimal counterexample at all. So it turns out that actually two joins are nicer than skew partitions, even though at first glance skew partitions are much more natural in this context. So now I can tell you theorem 1. So what theorem 1 says is, let G be a Besch graph, then either it admits one of outcomes 1, 2, 3, which means it's basic, or it admits one of the outcomes 4 and 5, so either it admits balanced skew partition, or it admits a two join, or its complement admits a two join. There's also outcome 6, which I'm not going to talk about because you don't actually need it. You can prove that you never need it. The reason I wrote it this way is two reasons. One is, historically, this is what we first proved. There was another outcome. Another reason is my PhD thesis was to prove that you don't need outcome 6. So I like to quote this theorem. So, but anyway, you can completely ignore outcome 6. Okay, so we proved that, and I convinced you that this is enough. And it's hard. The proof is 155 pages long. So let me say something about the proof. And like I said, I'm not going to do the details of all 155 pages. So it's hard to prove a theorem with 8 outcomes, right? You prove theorems, you know that. Because, right, you're trying to prove that your graph has a certain behavior, but you don't know which way to push it, which of the 8 behaviors you should be trying for. And some of the behaviors are sort of almost completely opposite. Like if you're trying to prove that this is a bipartite graph, you should be proving it doesn't have too many edges. If you're trying to prove it's a complement of a bipartite graph, you should be proving it has a lot of edges. So somehow it would be good to know which of the 8 outcomes, I guess 5 outcomes, depends how you count, you're going for. And there was sort of the big idea of the proof. Let's break the world into cases so let's assume something is present right, so I have a Besch graph and I'm trying to prove the structure theorem for it. Let's try to assume that something is present in this Besch graph that stops some of the outcomes from happening. And then, so now instead of proving a theorem with 8 outcomes, I'm proving a theorem with fewer outcomes, which is helpful. And the first thing of this kind that we ever proved was assuming that this is present. So this 8 vertex graph. So the theorem was if a Besch graph contains this 8 vertex graph, then it admits a balanced Cue partition. Right? You don't need anything else. There's only one outcome, just a balanced Cue partition. Now, some of the outcomes I can explain to you why they go away. So for example, in this graph, you have a triangle, right? If you have a triangle, then definitely it's not bipartite. Right? If I have a graph that contains this, it's not bipartite. There's a stable set of size 3, right? 3 vertices with no edges between them. So if you contain this, you're not complement bipartite. It contains what's called a claw. A claw is a vertex with 3 pairwise non-adjacent neighbors. So this guy, he's adjacent to those 3. That's a claw. And in a line graph, you can't have a claw. It's not hard to see that. So if you contain that, you're not a line graph. It contains the complement of a claw. So if you contain that you're not the complement of a line graph, and you can also convince yourself that this is not a double split graph. So none of the basic outcomes can happen. If you contain this, none of the basic outcomes is possible. So that's already pretty good. We rolled out the first three. Now, why you don't need two joins, that's a miracle that I can't explain to you. That's just you prove a theorem that says you don't need two joins, you only need skew partitions. But the way the skew partition situation works here is very nice. So if you look at this graph, you can see that it by itself admits a skew partition. Maybe let me draw it a bit better. So here's this graph I started with. And now you remember what a skew partition is. So we have A and B, and they're complete to each other. Can you see this, or should I draw it higher? Anybody? Let me ask it differently. Does anybody not see it? I know it's a difficult question. Okay. And then I have C and D with no edges between them. So if I call this A and those B, and those C and this D, that's a skew partition of this little graph. And now actually what you prove is that this skew partition extends to the whole big graph. You can give rules that say, put this vertex in A, put this vertex in B, put this vertex in C, put this vertex in D, and prove that the skew partition extends. For example, if I have, if I have a vertex that's adjacent to this and non-adjacent to this and non-adjacent to that. So what should I do about it? Well, it certainly cannot go into A because it has a non-neighbor in B, cannot go into B because it has a non-neighbor in A, cannot go into C because it has a neighbor in D, so it must go into D. And you make rules like that, and it works. It's always tempting to make rules like that, but it never works. Usually there's like, something else clever that you need to do, but here it just works. So that's this. And the whole proof is, you assume something is present that forces your graph not to be in too many basic classes. And then you prove a theorem that either you're in this one basic class that this graph allows you to be in, or you admit a decomposition. And then you're on to the next step, and at the next step, you're not thinking about the general Bear graph anymore, you're thinking about the Bear graph that doesn't contain something. So somehow it goes like that. Okay, so that's what I'm going to say about the long proof. Now, remember I mentioned that really any triple of theorems like this would work. And a few years after the strong perfect graph theorem was proved, Paul Seymour and I were able to come up with a simpler triple. Now, it's simpler in the sense that the proof is easier, the theorems are harder. I mean, not the theorems are harder, but the statements of the theorems are more complicated. So what we did was we added 2 more decompositions. And then when you have more stopping points, the proof's going to get easier. So let me tell you what the decompositions are quickly. One decomposition is something called an even pair. So what an even pair means, it's 2 vertices so that all induced paths between them are even. Even means even number of edges. And it was known for a long time that the minimal imperfect graph cannot have an even pair. And then the other decomposition is something called a dominant pair. So that's a non-adjacent pair of vertices that dominates the graph, that everybody in the graph is adjacent to one of these 2 vertices. And again, this was not known before, this just we made up because the proof didn't work without it, but it's not hard to see that this is a useful decomposition. It cannot occur in a minimal counterexample. And so now we proved this theorem with, like I said, more outcomes. But on the plus side, the proof is only 100 pages. But it's actually better than it sounds. So in the 150-page proof, the first 100 pages sort of follows the intuition that I described. You assume something is present that stops your graph from being in too many basic classes, and then you prove that it's what you expect. Either it's in the basic class that he's still allowed to be in, or it has a decomposition. And then you assume something else that is present of the same type, and you prove the same kind of theorem. And you go on like that, and then you get roughly to page 100. And then somehow all intuition disappears. You can still keep proving this complicated technical theorems to kind of push it enough to prove the structure theorem, but we could not develop any intuition for it. And it's scary when you have a proof and you don't have an intuition for it, right? You never know when you made a mistake in a little detail. If you somehow see some big picture, even if there's a mistake in a detail, you can fix it. But if you don't see a big picture, you're just going on doing calculations, that's not a good proof. So we're very pleased because we got rid of that part. We no longer have that part where we didn't understand why the proof works. So the way I like to describe it, we cut a third in length, but 80% in uncertainty. So that's good. Okay, so there are now two proofs in some sense. All right, so that's about the proof of the strong perfect graph theorem. Now let me go on and talk about some other problems related to perfect graphs. And one question that was open alongside with the strong perfect graph conjecture is designing an efficient algorithm to test perfect graphs. And efficient means that runs in polynomial time as a function of the number of vertices of the graph. And this is a natural question because remember I showed you this slide that said perfect graphs are nice, and one way in which they were nice was that they're problems you can solve in polynomial time. Now it would be nice if you didn't need to promise me the input is perfect. If I could test by myself if the input is perfect and tell you, sorry, I can't do anything, this graph is not perfect. So that's this algorithm to test for perfection. So I want to talk about it a little bit because it's nice. But one sort of striking thing about it, so you might try to test for being perfect and you might try to test for being bearish. And somehow it's probably easier to test for being bearish because being bearish just means you don't contain these particular structures. It seems easier to test whether you contain structures than to test, is the Clique number and the chromatic number the same? I know that's my intuition. I suspect that's most people's intuition. So after the strong perfect graph theorem, testing for being bearish and testing for being perfect became the same problem, which was nice. But that's the only way in which the strong perfect graph theorem plays a role in this algorithm. So in fact, this algorithm could have been proved, a long time before, it just somehow wasn't. Now you would think when you have a structure theorem, even if it's not like a complete characterization, but still some theorems that says either a graph is basic or it falls apart in some way, the way to get a recognition algorithm would be to use a structure theorem. And we're going in that direction, we're trying to prove that, except because it's not a complete characterization, it doesn't completely work. But in the end we sort of had some clever tricks and we could do it. And then it turned out that every time we used the decomposition theorem, we didn't need to use it. There was a much simpler thing you can do just from scratch. So in the end, there's an algorithm that doesn't use any decomposition theorems. And let me just give you a little glimpse into this algorithm, just for fun. So one thing in which it doesn't use a strong perfect graph theorem, but it uses the same kind of approach. We don't directly test for bearishness, right? We don't directly test is there not an induced odd cycle or is there a component of an induced odd cycle. We test for simpler things first, just like with the strong perfect graph theorem. First you assume this is present, then you assume this is present, then you assume this is present. Same thing here. First we test that something called the pyramid is not present. So first we check, well, let me tell you what the pyramid is. So a pyramid is a graph that consists of a triangle and a vertex, and there's 3 paths from this vertex to the triangle, right? So you can see why this might be called a pyramid. This is called the base. This is called the apex. And the rule is that only one of these paths is allowed to have length 1. Now, why am I making this rule? So I claim a bearish graph cannot contain a pyramid. Because why? Look at these 3 paths. 2 of them have lengths of the same parity. Let's say this and that. But then you go around like this, and that's an induced odd cycle. Right? Now, if I did allow more than one path of length 1, then this odd cycle might be a triangle, which doesn't help me. So at least 2 paths have interior vertices. And then the theorem is G beige implies G has no pyramid. Right? So, okay, so the first step in this algorithm is to test for pyramids. If I find a pyramid, I can stop and I can say the graph is not beige because of this theorem, of this very easy theorem that we just proved. If I don't have a pyramid, well, I'm not done yet, but at least, you know, my life got a little bit better. I restricted myself to a smaller class of graphs. I restricted myself to a graph without pyramids. So now, you know, it's easier to deal with. And let me maybe show you one other small step of the proof. Okay, so how do you test for a pyramid? It turns out that pyramids have this magical property that I'm really interested to know which graphs have this property, but I don't have a general answer. It's just, it so happens that some graphs do. So it turns out that if you guess these three vertices, and you guess this vertex, actually let me not say guess yet. So let's take, we have a graph G, and let's look at pyramid P with as few vertices as possible. And then you look at these three vertices and that vertex, and also take the midpoints of the path. Right, so this is so far 9 vertices. And so let me be safe. Let me also guess his 3 neighbors. I don't remember if I need it or not, but let's do it. So then it turns out that however you take a shortest path here, and 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 a shortest path there, you're going to get a pyramid. Right? That's not clear at all. Just because the white thing was a pyramid, if I take a shortest path between these two, it's not clear at all that I'm not suddenly going to get, you know, edges between them that I'm not supposed to be getting. But it turns out it's true. Now, why is it good algorithmically? Because then, in order to test for pyramids, what you need to do is go through all 10 tuples of vertices and see, can this 10 tuple be those 3 red vertices? And how do I see that? I take the 10 tuple and I calculate 6 shortest paths, which I can do in polynomial time, and I check is that a pyramid. And the theorem tells me that if there was a pyramid, and for some 10 tuple, this 6 shortest paths would give me a pyramid. Right? That's, I mean, that's a very nice property, and like I said, not all graphs have it, but some do. We call it the shortest path detector. And it's actually, I mean, there is, I mean, at least I wrote several papers that uses this technique, and I know that other people wrote more papers that use this technique. So somehow it's something general, but we don't know where its boundaries are. So anyway, so that's how you test for pyramids, and let me not talk anymore about the algorithm, but there's actually another place where you use a similar kind of idea that there are only, you know, a few important vertices and you guess them, and then you can just fill the rest with shortest path. So that's algorithm. Moving on. Given a perfect graph, find an optimal coloring. Again, whenever I ask an algorithmic question, what I mean is in polynomial time. Now, if you remember what I said very early on in my talk, this is actually done. You can do that. But the thing is, it's the way you do it, you turn the problem into a semi-definite program, and then you use the ellipsoid method to solve it. So somehow, as a graph theorist, I'm not satisfied. I would like to see, you know, it's a graph theory problem. I would like to see a solution in terms of graphs. I know I said to somebody yesterday I would really like to see some techniques in graph theory, so I guess I'm contradicting myself here, because this is an example of a technique in graph theory and I'm saying this is not good enough. But anyway, I'm allowed to have 2 opinions. Graph theoretical algorithm, an algorithm that doesn't use techniques from combinatorial optimization, that given a perfect graph finds an optimal coloring. So that's open. And again, we do have a decomposition theorem. It's not a complete structure theorem, right? It's not a theorem that says here's how you build the most general beige graph, but we do have some decomposition theorem, and you might try using it. So how would you use it? You would take your graph and you would decompose it using the decompositions, and then color the 2 halves. Right? So you decompose it using the decomposition, color the 2 halves, and prove a theorem that says you can put the two colorings together to get the coloring of the graph you started with, right? That's how you use decompositions algorithmically. And it turns out that you can half do it. If the decomposition you have is a two-join or the complement of a two-join, then this idea works. But if the decomposition you have is a skew partition, then this idea doesn't work. And I mean, if you think about it for a minute, let me remind you what a skew partition is. Right, so skew partition means the graph looks like this. It's partitioned into 4 sets. All the edges here present, all the edges there are not present, are missing. So it's not even clear how to partition this into 2 parts, right? What are the natural 2 parts to try to color? Not to mention, you know, how do you put the 2 colorings together? So skew partitions are bad. Now, I said 2 joins are good, and what do I mean exactly? So it's this theorem. If you have there is an algorithm that colors graphs that don't admit balanced skew partitions. So if I give you a graph, it's perfect, and I promise you it doesn't have a balanced skew partition, then you can find an optimal coloring. Now, how does that work? Let's see, my next slide is not better. So what I would like to say is, here's my graph, break it into 2 parts, color this, color that, you know, recursively or inductively, or depends which discipline you come from. And I told you because the way I broke G into 2 parts was via 2join, I know how to put the 2 colorings together. The problem is, what if this suddenly has a skew partition, right? My recursion or induction only works for graphs that don't have balanced skew partitions. So the main part of the proof of this theorem is to say that if you start with a graph without a skew partition, you can, and it has a 2join, then it has a 2join so that the parts don't have skew partitions either. So this is somehow the hard part of the proof, to deal with the fact that your inductive hypothesis needs to be more restrictive. But in any case, you can do it. I know it's a long paper, it's like a 50-page paper, but you can do it. So there's some other things, some other cases you can do. For example, there's a polynomial time algorithm to color perfect graphs without a square, without a C4. There's a polynomial time algorithm to color perfect graphs that have bounded clique number. And so here, there might be skew partitions, right? It's not like in the previous case where I had a nice decomposition instead of a bad decomposition. Here, there might be skew partitions, but the technique is the same in both places. What you prove is that you can find a sequence of skew partitions that you can keep applying them to your graph. So here's one skew partition, this is another one, so on and so forth. And in the end, do you understand what this tree is? It's not a tree in the graph, it's a decomposition tree. You start with a graph, you break it into 2 parts. Now each of these you break into 2 parts. Each of those you break into 2 parts. So you get what's called a decomposition tree. And you keep decomposing until all your graphs are simpler in some sense. And I'll explain in a minute what that means. But basically simpler means I know how to color them. And you would like to say, this tree is not too big, there are not too many of those. Right? I mean, one thing I can try and do is, every time I see decomposition, every time I see a skew partition, decompose. Keep decomposing. Okay, so it's true that I'll get leaves that don't have skew partitions, but the problem is I'm going to get a lot of them. Right? If there's exponentially many skew partitions, I'm going to get exponentially many leaves, and then what am I going to do? So in both of these situations, in both of these theorems, you can prove that you don't need to use all the skew partitions, you need to use some skew partitions, and then this tree has polynomially many leaves. This tree is polynomial. And let me just show you a little bit of that. So in the C4 free case, it's nice. So in the C4 free case, instead of using a skew partition, you use something slightly different, which is a decomposition where the cut set is 2 cliques. So your graph looks like this. A, B, and then there's so there are no edges, let's call them C and D. There are no edges between C and D, but what you need to do is delete is just the union of two cliques. And if you can prove that if a graph doesn't have this kind of decomposition, then it's easy to color. So you keep decomposing via those. Now, why should that stop? Why can't this go on for too long? Well, let's count the number of stable sets of size 3 in a graph. So I know there's at most n cubed of them, right? If n is the number of vertices, then the number of stable sets of size 3 is at most n cubed. Now I claim every time I decompose like this, I ruin one of them. So actually that's not completely clear, but you can demand that. But the point is, there is no stable set of size 3 in here, right? 2 cliques does not contain a stable set of size 3. So if I keep decomposing, and in every decomposition node, I ruin a stable set of size 3, but I never double count a stable set of size 3, then how many times can I decompose? Well, n cubed, as many as there were stable sets of size 3 when I started. So with this invariant, you can prove that your tree only has n cubed internal vertices, so only n cubed leaves, and then that's exactly what you wanted. And so that's, in this case, it's basically the same, except what you count is much more complicated, so I'm not going to tell you about it. Now, I conjecture that something like this is true in general perfect graphs, that there is a set of skew partitions, which is not too big, and you can decompose via them, and only get polynomially many leaves that don't have skew partitions, or maybe don't have these special skew partitions, and then you can color them. I know I had some ideas on how to prove it, and none of them worked, but I still believe the conjecture. I just think my proof didn't work. So anyway, but that's a question I'm very interested in at the moment. Is it true that you can find this special set of skew partitions that allows you to decompose a polynomial, decompose a perfect graph into, with a polynomial size tree? Okay, so the next part of my talk is related to things I'll talk about tomorrow. And so this is just kind of an introduction, and then tomorrow I'll do the details. Okay, so what were perfect graphs? Perfect graphs, we were trying to understand when are chi and omega the same. And we did. Right? So we know all the minimal imperfect graphs. We don't have a construction yet, but we know a lot. Now, what if I weren't quite so greedy? What if I didn't say I want chi and omega to be the same? What if I was just interested in trying to bound chi as a function of omega, right? To say chi is at most omega squared, or 2 to the omega, or 2 to the 2 to the omega. What can I say about graphs that have this property? So a graph is called, a class of graphs is called chi-bounded. A class of graph is called chi-bounded if there is such a function that works for the whole graph. And for technical reasons, I only want to think about classes of graphs that are closed under taking induced subgraphs. Right? If a graph is in, then all its induced subgraphs are in. So a class is chi-bounded if and only if there's a function like that. And if you want to think about chi-bounded, it's only an interesting question for infinite classes of graphs. Right? If you have a finite class of graphs, then just take f of omega to be the maximum of the chromatic numbers, and that works. So this is only an interesting question for infinite classes of graphs. Finite graphs, infinite classes of them. So the first question is, maybe there's a nice theorem that says chi is at most f of omega for all graphs. But the answer is no. There's a construction of Michalski that I'll show you the details tomorrow. He constructs graph with clique. He constructs an infinite family of graphs, each with no triangles, so it's clique number 2, and where the chromatic number goes to infinity. So the case member of the family has chromatic number k. So that means, right, if there are graphs with arbitrarily large chromatic numbers and clique number 2, that means there's no chance of getting of getting this kind of function that works for all graphs. So then we want to think about, we want to ask the question, which graphs are chi-bounded, which classes are chi-bounded? And the first candidate is forbidden induced subgraph. Who knows, maybe that would work. But very quickly you see that it wouldn't work, because take the subgraph you forbid to be the triangle. Right? Forbidding a triangle, you have the whole Mischewski family again. The Mischewski family doesn't have triangles. So this is false too. And in fact, Erdős proved the theorem, which is much stronger than Mischewski theorem. He proved that, so Mischewski constructed a family of graphs with no triangles and arbitrarily large chromatic numbers. Erdős proved that there are graphs with no short cycles and arbitrarily large chromatic numbers. And short is, as long as you want. No cycles of length at most 100 and arbitrarily large chromatic numbers. No cycles of length at most 1,000 and arbitrarily large chromatic numbers. And that means that if I were hoping that the graphs I get by forbidding H is a chi-bounded class, H shouldn't have any cycles, right? Because H is just one graph. Let's say it has 100 vertices. If H had a cycle, then the class of graphs with no cycle of length at most 100 would not contain H. Its members would not contain H, and yet I would have graphs with arbitrarily large chromatic numbers there, but Clique number only 2. So if for H is chi-bounded, then H shouldn't have any cycles. And there's a conjecture that's if and only if. It's a conjecture of Jeffers and Sumner that if H has no cycles, then forbidding it gives a chi-bounded class. And it's hard. It's been open for, so Jeffers made this conjecture in 1967, and Sumner made this conjecture independently in the 1970s, but it's still open. And not only is it still open, very little is known about it. Again, it's one of those conjectures people are thinking about, not as much as about perfect graphs, but enough. And very little is known. So Jeffers himself proved that it's true for a path. If the class of graphs that with no long path has, is chi-bounded. Then Kierstead and Penrice proved it for trees that look like this, trees of radius 2. Alex Scott proved the topological version of it. So what that means is, instead of forbidding one tree, you fix a tree and you forbid all its subdivisions as induced subgraphs. So you forbid an infinite family of graphs, but somehow they're all related to one tree. So you get a chi-bounded class, and then recently with Alex Scott and Paul Seymour, we proved that trees like this work. But again, it's tiny little bits. I don't know. I mean, it's a little bit strange. Maybe it's false. So that's the Jeffers-Sumner conjecture, which I won't talk about much. But let's think about something else. Let's think about forbidding some cycle lengths, induced cycle lengths. Right? In the strong perfect graph theorem, we forbid odd cycles, we forbid complements of odd cycles, and we prove that chi and omega are the same. Now, what if I just forbid induced cycles of certain lengths? So I'm not hoping to prove that chi and omega are the same because I know the strong perfect graph theorem, but I would like to know what lengths I need to forbid in order to get a chi-bounded class. Okay, first of all, you need to exclude the infinitely many lengths, right? Because if all the lengths are excluding are at most 1,000, then again, by Erdős's theorem, there's a class of graphs, there are graphs with no cycle of length at most 1,000 and arbitrarily large chromatic numbers. So that's not going to work. And in fact, you can show that not all infinite families work. There are some, you could conjecture, however I exclude an infinite family of cycle lengths, I get a chi-bounded class. And that's not true. That's not true. But Jeffers he made several conjectures about what lengths you need to exclude to get chi-bounded classes. And recently with Alex Scott, Paul Seymour, and Sophie Sperkel, we proved the strongest of them, which implies all the others. So what it says is, if you forbid long odd cycles, then you get a chi-bounded class. So long is however long you want, right, for every number L. You allow any cycle of length less than L, and you allow all even cycles, but you don't allow any odd cycles of length bigger than L. then the class you get is a chi-bounded class. And the function that works depends on L, but for every L there is a function. And that's, I'm going to talk about this theorem tomorrow. So that's sort of a very quick introduction to chi-boundedness. And now let me mention another problem that I won't talk about tomorrow, but it's a problem I like, so I want to talk about it a little bit. So some of you may know the graph minor theory. And what that says is that if you exclude a graph as a minor, then you get a structure. Right? For every H, graphs that don't contain H as a minor either can be embedded in some surface or can be obtained from graphs that are embedded in some surface. So somehow it's all nice. And it would be nice if something similar happened if you forbid an induced subgraph instead of a minor. So that's, I don't know if it's true or false, but certainly we're nowhere near understanding how that could possibly be true. But it would be nice to ask some question where if you forbid, for every H, if you forbid H as an induced subgraph, then something. And I only know one conjecture of this form, and that's the Erdos-Heinel conjecture. So what the Erdos-Heinel conjecture says is that for every H, if you forbid H as an induced subgraph, then suddenly you get either a surprisingly large clique or a surprisingly large stable set. And how large? So I forbid H. Right, I have a big graph G, and I tell you it doesn't contain H, then the conjecture is that G contains a clique or a stable set which is this big. The number of vertices of G to the power, to a power that depends on H. So that's large. Now, why is it surprisingly large? Because if I don't forbid anything, then all I can hope for is log the number of vertices. So somehow, what this conjecture says is that if I forbid an induced subgraph, something global happens to the graph, right? I forbid an induced subgraph on 7 vertices, so that's a very local thing to do, right? It's just to say, examine all seven tuples of vertices and something happens. But the conjecture is that it has a global effect, which is that, a clique or a stable set of size, the number of vertices to some power. Sorry, wrong way. And this is just to make talking about it a little bit easier. So I want to say H has the Erdos-Heinel property if the Erdos-Heinel conjecture, H has the Erdos-Heinel property if there is a delta so that every H-free graph contains a clique or a stable set of this size. So the Erdos-Heinel conjecture says every graph has the Erdos-Heinel property, right? But it's just, it's a convenient way to talk about it. So now I can tell you which graphs are known to have the Erdos-Heinel property. The conjecture is that all graphs do. But what's known is actually very few. So we know that graphs on at most 4 vertices have the Erdos-Heinel property. We know that this graph, which is the bull, has the Erdos-Heinel property. And then there's a general theorem of Alon, Pach, and Shor-Moshe that says that if 2 graphs have the Erdos-Heinel property, then substituting one in the other gives another graph with the Erdos-Heinel property. And what that means is, so I'm going to tell you what it means to substitute F in H. So I have a graph H, and I choose, so actually, substituting F in H for V. And I'll explain what all this means in a minute. So here's a graph H, here's its vertex V. And here's another graph called F. So then to substitute F in H for V means, so V has some neighbors and has some non-neighbors, right? So now I take a copy of F, and I make F adjacent to all the neighbors of V, and I make it non-adjacent to all the non-neighbors of V. Right? So I replace V by a copy of H. So the Alon-Pach-Shor-Moshe theorem is that if you have 2 graphs with the Erdos-Heinel property, then you can substitute one in the other and get another graph with the Erdos-Heinel property. So then the question becomes, which prime graphs? Prime means you can't get it by substitution. Which prime graphs have the Erdos-Heinel property? And for that, the bull is the biggest known one. Right? So we have graphs of size at most 4, and then the bool. And just to sort of give you an idea of how bad things are, here are open cases, right? Here are graphs for which we don't know if they have their channel property. C5, the complement of a 4H path, 4H path, 5-vertex path, and the 5-vertex path. So these are, really tiny little graphs, and yet we don't know the answer. It would be, proving that any of them has their channel property would be a really good result. Even proving that excluding 2 of them gives you a big clique or a big stable set would be a good result, except if you exclude this and that, then that's known. But like excluding C5 and a 5H path, proving that you have a big clique or a big stable set, that'd be great, that'd be wonderful. So anyway, so there's a lot to do. Thank you very much. I'm going to stop here.